Welcome to this week's VLSI Insider. This is Dan Hutchison.
This is Andrea Alati.
And this is Jason Haupt.
So it's been kind of a quiet couple of weeks, but we did finish our forecast. And Andrea, you have a pretty spectacular forecast for the equipment market this year.
Yes, we did upgrade the equipment to about 42%, which is something that we did actually almost last month. And the IC forecast, it's pretty much coming along where we expected. We're still forecasting a 26% growth year over year. All the data that we've been getting lately is pretty much matching our numbers. The Taiwanese data for August actually was still very, very strong, especially if you look at the memory area. Actually, memory prices, especially on DRAM, if you look at sales, they are accelerating. I think Nanya's revenues on yearly basis in July were about 50%, and then in August about 60%. So again, pretty healthy numbers. The only thing that I'm a little bit worried is that if we look at spot prices, especially for DRAM, it continues to be very weak, right? So there has always been this lag between spot prices and contract prices, with spot prices leading contract prices. So if we look at the spot market, actually prices there are falling at 2 to 3% a week, which is quite high. And it's something that we have to worry especially about next year, because if that continues, that means that at some point contract prices will have to reset and match whatever is happening at the spot level. So, and I think that's one of the reasons why memory stocks have been quite weak in the last month or so, is because of this fear that perhaps next year we're going to see a rollover in pricing, especially in the DRAM side. But again, it remains to be seen because, you know, not all the cycles are the same, as you know, so we'll have to see once we get into next year.
Yeah, so that's been kind of interesting. What about, you know, last time we talked about DRAM prices and spot prices and the CPPI, because the CPPI has gotten pretty scary lately, but that's not showing up in the contract or the WSTS numbers, right?
No, not at all. And actually, if anything, we're still seeing sort of an acceleration of strength on the contract level, right? So, you know, this gap actually is quite big. So it's more, and I think there is still enough momentum this year for the contract prices to be pretty healthy. It's more what happens next year, if these things will need to be in phase. And if they are in phase, then that would mean that contract prices have to roll over. And if that happens, I think we'll probably see the sales begin to soften, because again, pricing is really what drives most of that sale momentum. So again, it remains to be seen, but there is quite a bit of a disconnect between these two points.
I think something has to happen with contract prices too, just because of the fact that notebook prices and PC prices are down and off so much.
Yes, and that's the other part that I still think that there has to be a correction along the way, because if we look at sort of the end market, right, we are seeing plenty of availability there. And also, you know, we don't see that tightness that we saw earlier in the year or even last year. So I think at some point we'll probably have to see these pricing pressures roll at the contract level as well.
By the way, there's this Boston Consulting Group study that's been circulating around that says that 44% of the world's semiconductor manufacturing was in Europe in 1990. I think it's a backward extrapolation, but I don't know how they arrived at it. But there's no way it can be 44%, because I remember Japan was a huge percentage back then. And the battle was mainly between Japan and the US, and people were talking about Europe's loss of manufacturing share back then. You were telling me earlier, you got a couple numbers on that?
Yes, I mean, they're still rough numbers, but I think they're fairly accurate. If we look at the early 2000s, right, Japan actually was about 30% of total manufacturing. North America was about 20%. Asia Pacific, which includes primarily Korea and Taiwan, was 35%. And Europe was only 15%. So Europe actually was the smallest back in the early 2000s. So I'm wondering,
in 10 years, that would mean they had lost they've gone from 44 to 15. They lost 30%, and that doesn't make sense to me either.
No, I doubt it. Unless, again, they're talking about a specific part within that capacity. But yeah, Europe, it's close to 15%, and it has lost some shares since then. But I'll be very surprised, to know why that number is so high. The number is being quoted 44%, because it's a really high number.
So, Jason, you guys been doing a lot of work in memory lately, and I want to know who's on first in memory.
Oh, wow. So it's been a wild ride. I mean, the last few years has seen such amazing innovation scaling like we've never seen before. And what we've seen in the last couple of months is Micron continuing with a very commanding lead in that space. And if we take a look at where they are in DRAM right now, they came up with their D1 Alpha. And what does that mean? I mean, we're all kind of moving away from talking about nanometers, but if you were to sort of use the old metrics, it'll sort of be in the 14 nanometer range. So really, it's the most advanced DRAM node out there, and that continued with their latest flash offering. We're seeing 176 layer 3D NAND flash and it's well ahead of where even Samsung is. It's fantastic to watch. So that's all. I mean, all good, and we're hearing a lot about what's happening there. An area that doesn't get talked about very much, but I think is going to be much more important in the coming couple of years, is something that we actually saw out of TSMC just in the last month or so. We were having a look at a Fitbit product, and there's a processor inside. And what we found is not only MRAM, so non-volatile memory embedded in the processor, but in fact the most advanced node that we've seen by a long shot, down to 22 nanometers, which means that the density is getting to the point where it goes beyond just sort of niche applications in industry and actually used for consumer goods like the Fitbit. And we're just going to see that expanding. The other interesting part is that the change in technology we're seeing in MRAM.
Yeah, one thing is
yeah, of course,
it tells you on the Fitbit that the cost of 22 nanometer is getting to the point, the design cost, that you can squeeze it into a market size of a Fitbit, right? So it says that the leading edge technology is really getting cost effective at that level.
Absolutely.
Even though today 22 nanometer is what, 3 nodes behind, 4 nodes behind, but it's
for
still
sure
advanced.
Yeah, absolutely. And if you take a look at the bulk of consumer goods, they're not at the leading nodes. We spend a lot of time in the media talking about the latest Apple processor, Samsung processor, but the reality is it's a very advanced node. Yes, it's 3 generations behind, but it's very, very, very capable. And now with this MRAM, not only did they get the density and the shrink, but they've moved over to something called spin torque transfer. It used to be something called toggle, but the spin torque transfer technology has at least the possibility, the capability of being like an order of magnitude or better in terms of power consumption on write cycles. It used to be fairly power hungry when you wanted to write to an MRAM. Now it is really power sipping. And so beyond the sort of larger scale applications, we're going to see this popping up in IoT applications where there's remote sensors and you need this non-volatile memory. The other advantage, of course, to MRAM over, say, flash is its write tolerance. You can do thousands of times more write operations to an MRAM than you could for a flash. The flash would break down. The MRAM will not. So again, for a long-lasting, high read-write application, we're going to see this a lot more in the future, and it'll become that much more important.
Well, plus it doesn't really require a lot of extra costs in terms of mask layers and things like that.
It really doesn't. It's implemented at sort of the slightly upper layers within a processor or a controller chip. And I mean, relatively inexpensive to implement. And so, as you said, the Fitbit is by no means an ultra premium product like the latest iPhone or Samsung Galaxy phone, and it's cost effective. So this is a technology for us to watch.
What's interesting is the technology to manufacture it was developed, with Applied Materials and their tool sets, but a lot of the foundries have been talking about implementing MRAM for a while now. I mean, it's been on their roadmaps. To me, it's fascinating that it took this long for you to find one.
We've seen MRAM before. Again, it tends to be in niche applications and lower density applications. It's not sort of the leading edge, if you will. It's really now, I think we're just at that turning point where it's passing that threshold. I mean, Dan, you and I were talking a little bit beforehand about the adventures of phase change RAM and some of the challenges there. And some difficulty in getting traction in the market and seeing it in a lot of products. I think this is an indication that we're sort of beyond the challenges and we're ready for mainstream and MRAM.
Yeah, what's also interesting about it is if you think about when you go off chip to another chip, it costs you about a couple orders of magnitude, maybe 3 orders of magnitude in power. And if you're putting something out there like a remote sensor that you want to stay out there and just go for forever with on a battery.
Absolutely. And from a performance standpoint, of course, the closer you can put your memory to the processing engine, the much quicker it is to get that data transferred back and forth. So you actually get a performance advantage as well. Yep.
Okay, that's cool. So I know we didn't talk about this before, but any more cool things that are coming you guys are working on that we should be paying attention to?
Yeah, so there's actually quite a bit going on in the power transistor domain, and we might have touched on this a couple of weeks ago. But there's just this really fascinating war going on between silicon carbide and gallium nitride, and every week what we're seeing are these sort of continued indications of one sort of stepping over the other. But silicon carbide is really it's quite mainstream, but gallium nitride is taking off like mad. So this is something that we're watching very closely, and we're honestly we're challenged. When you take a look at things like data sheets on these kinds of devices, they're all selling slightly different variations. It's hard to kind of normalize. And so something that we're working on right now is actually a normalization to do real one-for-one comparison from a cost versus performance standpoint. And I think that's something that would be worth us talking about in the coming weeks.
Yeah, any particular companies in the lead there?
So, and there are so many players that are in this space. One of the ones that we're actively watching actually is a small company called GAN Systems, and they're actually based in Ottawa, Canada, where I'm located. Now, of course, they're working with a foundry partner, but we're seeing some really interesting performance out of what they're producing. So stay tuned.
So watch GAN Systems, huh? Hey, thanks a lot. I appreciate you taking the time today. And Andrea, same.
You're welcome.